then depending on the strength of the magnetic force, you could say at each point within this domain, right, there is some pull in that direction, or push, however you want to look at it, okay, in this direction. And the direction, of course, the vector's going to give you both the direction and then the length, right, as a magnitude. So the length of the vector tells you like how strong the force is, and then the angle would give you the direction. And if you imagine that at every point, then you get where those iron filings kind of follow the vector field. Right, so you would not expect to see this, right? At this point, you would not expect to see that vector, right? That vector should be running kind of in line with the way things appear to be kind of flowing, right? Does that all make sense, y'all? Another example is if you take like a hill. Sorry, it's so blurry. I don't know why I haven't replaced this. This is like a hill, right? Like a hill and a valley and a hill, right? If you look at that from the top down, it would look like this. This is called a topographical map. So what it does is it gives you like this hilltop up here, and then like wherever you have a constant elevation, you draw a ring. The next elevation down, draw another ring, and then another ring. So this is a topographical map. And so if you were to imagine this as being our D, then you could take at any point, you could let a vector represent like maybe the direction that you would go if it was a ball that you just dropped there. Just put a ball, let it go, and then the vector could be pointing in that direction of motion. And then the length would be, if it's real steep, it would be long vector. If it's kind of flat, it would be a short vector. Yes?
Would gradient vectors work in this? Or no?
Yeah, so that's coming. It's like, what's the most natural vector field to have? It would be the gradient vector field. But we'll define that at the end of the section. So there's kind of that same idea, but on a different map. That's a vector field, right? So topographical map, dropping things down, shows you kind of like how steep the hills are and directions things would roll. Yes?
That would be the question. What direction are they pointing at? Are they pointing at the tangent point of like a specific point, or are they pointing like at a specific thing?
No, it's a flat picture, right? So there is no, the vector field is in two-dimensional space. So all it does is gives you the direction, right? Direction and plane, and the length tells you how strong that is, or if you were back on the hill, like this is a bunch of hills, right? If you look at it from the side. And then if we're looking at it from the top, then if I put a ball right there, it's going to want to go like down that hill, right?
Okay.
And so this vector is kind of showing you the direction, and then the length is like how steep. All right, so here's an example of a vector field where I actually, up to this point, I've just shown you what they are, right? But I haven't actually defined a vector field. So here's an actual vector field where I'm defining it. So just notice the notation that we have up there. We have capital F, right? The vector capital F of x, y. Look, this is a vector. We call this a vector function, right? It's a function that's going to spit a vector out. Now, what is it taking as input, though? What are you providing this vector function? Set of coordinates, x and y, right? So you're giving it a point in two-dimensional space, and it's providing you or spitting out a vector in two-dimensional space, isn't it? So technically, math majors, this is a function that goes from R2 into R2. It goes from two-dimensional space into two-dimensional space, which means that if you want to visualize it, you would think you need 4 dimensions, 2 for the input, 2 for the output. But because it's a vector field, I can take the output and just lay it on top of the input. And that's why we're seeing this, right? The input are these points, and the outputs are the arrows. Okay, so we are actually condensing the 4 dimensions into just 2. Technically speaking, it is a function that goes from R2 into R2. Now, this is the value of the function, negative y, x, okay, that's the value, or not the value, that's the definition of the function. So what this is going to do is, you give it a point, and what it's going to do, an x and a y, and what it's going to do is it's going to create a vector where the x component of the vector is the negative of the y coordinate, And then the y component of the vector is the x coordinate of the point. That's just the way I chose to define the vector field. So what would happen at 0, 0? Let's see, what happens if you take the origin and plug it in? You get 0, 0, right? You get the zero vector, right? And the 0 vector, you can see I have it right here. There it is. There's the 0 vector. Let's go to another point. What if I do, let's go down the x-axis. What if I go to 1, 0? What vector should I expect to see here? So negative of the y coordinate, so 0, and then 1. Let me show you that. So if I move to the right, there it is. If I go to the point 1, 0, the vector that comes out is the vector 0, 1. Does everyone see that this is the vector 0, 1? I mean, technically the vector 0, 1 should be right here, shouldn't it? But vectors can move around. So just translate it over to where the domain point was, the xy that got plugged in. There's the vector that comes out. And as I go to the right, let's say I go to 2, 0 out the x-axis. I would expect my y coordinate to stay 0, right? But I'm sorry, my x component to stay 0, but my y component is actually going to become the 2 now, right? So it's just going to become a longer vector as I move to the right, but still pointed up. So I'm going to start moving it. Just pay attention to see how I go to the right, and the vector still points up, just gets longer. Yes?
So it still holds respect to the magnitude of the original points?
Say again?
It still holds respect to the magnitude of the original?
It still holds respect to the
magnitude would be 2.
The magnitude of that vector is 2.
And then 3, 4.
What do you mean respective to the original points?
So like, let's say if I put 1, 1
Mm-hmm.
to the 1 square root, it would be that.
Are you saying like the length of this? Oh, well, this is a point, right? So I guess what you could say is for this scenario, the length of the vectors is the same as the distance from the origin to that point. You could say that.
This scenario.
For us moving out the x-axis, right? Now, what happens when I change and I go, I don't know, let's do something like 1, 1. So if I do 1, 1, right, the vector that comes out is the vector negative 1, 1, right? Negative 1, 1. So if I go to 1, 1, which should be right here, the vector I'm going to get out should go, what, left 1, down 1? So it should point like that. Oh, I wrote the, yeah, sorry. Yes, that's, again, left 1, up 1. Like that. Let me move it. Get it to 1. Let me move this to 1. There it is. Oh, hey, pretty good. All right. And for every single point in here, right? Every single point in here, we have a vector. So do you see it would be impossible for me to show you all of them because it would actually just fill the whole space up with vectors and you wouldn't even be able to tell what's what. But what we can do is we can have the computer give us some of them, not all of them, but some of them. And if we look at some of them, we can kind of get an idea of what's going on, right? So this is not every single point in the space, but it's enough for us to start to get an idea. Now, it's actually not drawing them to the correct size, but it is showing us the trend. So the trend is that as we go to the right, the vectors are getting longer, right? And if we move up a little bit, they start to tilt this way. And so you get, the further away you are, the longer the vectors are, the more closer to the center, they're smaller. And there seems to be almost like, think of this as like water flowing or something. If you were to just drop like a, I don't know, a little leaf or something on the water, it would want to go like this, right? It would just want to flow around like that. Now, if you get into the middle, it'd be slow, right? It'd be slower flow, but if you drop it out here, it's going to be a faster sort of rotation about the origin. That's that vector field, right? I can make up a completely different one. Any questions about this one? I have more vectors. That's just more vectors in there, okay? It just looks same. You can see the same characteristics. For this one, I have it where you can tell me what you want the vector field to be. Like, and I'll type it in and we can look at what it looks like. And you can come up with anything you want, all right? So the f of x, y, these two things in here are just have to be functions of x and y. And they don't have to be separated either. You don't have to have like just y's here and just x's here. You can mix them up. Totally up to you. So who wants to give me the first? What do you want here?
X plus y, y plus x.
X plus y. Well, you're doing one of them. Who wants to? You get the second one.
3y minus 2x.
3y minus 2x. Y'all are staying linear, okay? Y'all want to stay? You want to change it?
Yeah.
What do you want?
Make it tangent numbers. Yeah, I was going to say.
Oh, arctan or something?
Do it like a sine wave.
Let's do this one first. Let's see what happens here. X plus y, and then 3y minus 2x. Okay, so I'm just going to start moving this around, see what happens. Okay. It's like John Travolta, right? And then this way. Okay. Let's look at it. So that's definitely doesn't have that like full circular effect that the other one had. In fact, this is more of like a clockwise, as opposed to the other one looked counterclockwise. It does kind of seem like when you get further away, they get bigger. Okay, that's what it looks like. All right. Let me change this other one. Oh, you know what? I typed it in right. Let's square one of these. Yeah. So you see that? It seems like a little like almost like an arch effect there. Do y'all agree or not? See? We're at -2.
Like, as it's going up, they go opposite, like a line.
Yeah, there's like.
If you're negative.
We're at -2?
If you go up, the vectors are going like,
Yeah, that's weird, huh? It's weird. Let me move this around to see what it does. It's like dancing around. Okay, let me change this one. I'm going to make this one sine of x times y. I think that's an input error. Yeah, it's like, no, thank you. I have to type it in a certain way, or it won't understand it. Let's just do sine x. There we go.
Oh, we kind of got a sine wave in there.
Yeah, there's going to be a sine wave in here somewhere. Let's do sine x, sine y. Right? So you've got all sorts of, I mean, the possibilities are limitless here, right? All right, that's a vector field. It's a function that takes in a point in two-dimensional space and spits out a vector in two-dimensional space. That's it. Everything we just did can be extended into three-dimensional space, where your function now takes points in three-dimensional space and assigns to every point a vector in three-dimensional space. So now your capital F, right, takes in x, y, z, spits out a vector x, y, z, or some function of x, some function that depends on x, y, and z. So a good example is like this is a pretty cool little visual of the magnetic field for the Earth. So if you go to some point, right, then the magnetic field is going to be, going in one certain direction, and it's going to have a certain strength to it. And so at every point in here, there's some vector, right, representing the field, the magnetic field. But it's a vector. Here's an example, a specific example, -yx. That's the same vector field we had just a second ago, the first example I showed you. That's the same first component and second component, right? But now I have the third component, 2z. And that's what it looks like. Okay, this is it right here. At every point, there's some vector. I can put more in there, but then it starts to look crazy, right? Like you can't see. It just overwhelms you, right? Because there's so much in there. Yes?
Can we see from the top down?
From the top down, it should look exactly like it did a minute ago.
The circle.
Yeah, it's that same one that we saw in the previous. See, it's hard to see, but yeah, it would be the same one. Okay? I have more that I can actually move a vector around in here. Same idea, you move some x, some y, some z, there's some vector assigned to that point. Here's an example of gravitational field. Now this one is not exactly, this does not represent gravity on Earth because Earth is not a perfect sphere, and then also the Earth is not perfectly smooth on the outside, right? You got like, you know, hills and valleys and different elevations. So this is not exact, but it gives you the flavor of what a gravitational field should look like. So look at the field. First notice that this right here, square root of x squared plus y squared plus z squared, if you give me a vector, right? If you give me a vector, x, y, z, then if I ask you for the length of that vector, it would be the square root of these things squared and added up, right? So I'm giving you a point x, y, z, and the vector you're creating is x, y, z, but all of them negative, and then dividing each of these components by the length of the vector, which means the length of that vector should be what? 1, right? You're taking a vector and you're dividing it by its own length. And so you should get a vector of length 1, and because all of the coordinates are negative, here, let me draw it for you, it'd be a little bit easier. If this is x, this is y, and this is z, imagine that I take a positive x, a positive y, and a positive z. So I'm sitting here in the first octant, right? From the origin to that vector, I'm not going to break out my x, y, z, but you know, x, y, z, I go out, over, up. I have a vector from the origin to that point, right?
Yes.
That's the vector x, y, z. What I'm doing is I'm creating a new vector that is the negative of each of those, which means you're pointing that vector back towards the origin, right? Multiplying by negative changes the direction, and then you're scaling it to make it have a length of 1. So now it's a length of 1 vector pointed back at the origin, and that would be for every single point that would happen, and so you'd get a vector field that looks like this, a center-seeking vector field. At every point, it draws a vector of length 1 pointed back to the origin. And that's kind of the way gravity works, right? Kind of, not exactly. You actually would want that to change, right? Like the closer you got, you would want it to become stronger, right? And then as you get further away, you'd want it to weaken. But that's good enough for a lot of things, right? Because we can kind of look at the Earth as a sphere, like smooth sphere, and for most physics applications, it's good enough, all right? So yeah. So that's a specific example of a vector field in 3-dimensional space. All right, now, from that, if a vector field can pretty much come from anywhere, we have a place where we can actually create them. This goes back to an earlier chapter where we were talking about, this was chapter 11, where we were talking about gradients. And so I say recall back from chapter 11 that if you're given a function of 2 variables, right? So we call this a scalar function because you plug in a point, it spits out a number. So if you take that function of 2 variables, that would be a surface, right? That would be a surface. In 3-dimensional space, it would be a surface. So if you take some surface, then we can always calculate this thing called the gradient from back in chapter 11. And what it was, this was the notation we used. Gradient of f is a vector. It is the partial of f with respect to x, and then the partial of f with respect to y. That was this thing that we called the gradient vector. And do you all remember what the gradient vector always gives you? It gives you, yeah, the direction to point in for the steepest rate of change or steepest ascent. That's what the gradient vector always, and it was this really awesome thing that we were doing a directional derivative, and then we wound up saying, oh, but we want to be able to get the directional derivative to, go back and look at the proof for it. We wanted to get the angle, it had to be 0 to get cosine to be 1. We're using a formula for cross product. I won't go through it again, but we showed that the gradient vector always gives you the direction of maximum rate of change. So why don't we create that as our vector field, right? Like, why not? The gradient creates a vector, right? It takes in a point, spits out a vector. So let's use it. We could do the same thing in three-dimensional space. If we have a scalar function of 3 variables, then we could do the gradient of that, and that would create a vector field as well. That vector field has a special name. Not a very tricky name, but it's called the gradient vector field. Yes?
Did we go backwards or not?
What do you mean?
If you have like a vector field, could you?
Yes, so we have a good question here. So this is saying that if you give me a scalar function, right, I can create the gradient vector field from it, right? And I should be able to do that if someone gives me any scalar function, I should be able to create the gradient vector field. Your question is, if you have a gradient vector field, can you go back to the scalar function it came from, right? Something like that?
Yeah.
So if you're given a gradient vector field, you're told it's a gradient vector field, that implies that it came from a scalar. But a general vector field, right? A general vector field does not have to come from a scalar function. And we have a name for it. If you have a vector field that did come from a scalar function, it's called a conservative vector field. If it came from something else, not a scalar function, then it's a non-conservative vector field, which is important in physics because we like conservative vector fields in physics. All right, so, but we're coming to that. We're actually going to talk about that. So for now, if you're given a scalar function, how do we generate the gradient vector field? So here's our first mechanical example out of this section. Given this scalar function, find the gradient vector field. There's nothing new here. We've done this before. We just have a new name for it. So, oh, I forgot to show you the notation. Was there a notation here? Right here. That right there would be, that's our notation for taking the gradient of a scalar function. So I'm going to find the gradient vector field of this. I'm going to call it capital F. And what it is the gradient of the scalar function f. Right? The field I'm about to define is going to be the gradient of f. And the gradient of f is a vector that is made up of the partial of f with respect to x, partial to f with respect to y. And when I say f here, I mean the scalar function f, not this vector, capital F. And these should be pretty straightforward partials, right? I mean, we're kind of used to the partials by now. I hope, yes. So the partial of this with respect to x, I can ignore this. That's 2xy. And then partial of this with respect to y, that's a 1, that's a constant. And then here, just power rule, 3y squared. There it is. That's the gradient vector field. That's it. So what would happen here is that, again, if you were to graph this, this would be some surface up here, right? And then down on the ground, right, down on the ground here is your domain. And so if you take a point here, right, that corresponds to some point up here. Yes?
What's the trick?
What's the what?
Why is it so easy?
Why is it what so
Why is
easy?
it easy? Just like calculus.
Why is it easy? I don't know.
It feels like a hidden trick.
Well, yeah, hold that thought.
He's like, just wait till you drop.
Hold that thought. It's not necessarily hard. It's a lot of things to keep in order. I mean, that's what's going to be the challenge here, is keeping things in order. Yes?
So if we plug that into the vector field exercise thing that we did earlier, where we were just plugging in random
Yeah.
stuff, we would get its own little...
Yeah, it's going to have its own vector field. Now, I want to reiterate that a little bit, but let me get back to, I don't think this is necessarily harder in any way. But I also don't want to downplay it like, no, this isn't hard, this is easy, right? It's just the amount of information. So I alluded to this when we started this class. We're in 13.1 right now. These are the formulas for 13.2. Okay, these are all the formulas that we have in 13.2 for doing these things called line integrals. Okay, that's just 13.2.
So we're gonna get that on the file?
So yeah, I provide this to you. Yeah, you're welcome. Yes, you're welcome. Right. I don't remember when I was in Cal 3 if I had to. I don't think I had to memorize all this. This is chapter 3. This is the entire. I don't have it. Okay, this is the chapter 13. All the formulas for just chapter 13. Okay, this is everything for chapter 13. Formulas. That's just formula. That's not like the theory, the definitions. That's just formulas. So it's really a matter of you seeing a problem and knowing what to do because you have all these different things, right? So it's nothing is, I don't think, harder. Like the math's not going to get harder. It's understanding and organizing your ideas. So, all right, so back to this one. Back to what this is, right? So you have the surface above, right? This is an important distinction to make here. You have the surface above, right? And if imagining again like this was a ball, right? If I drop it, it's going to want to go downhill, right? The gradient doesn't give us the vector that gives you the steepest downhill. It gives you what? The vector of the steepest uphill, right? So this is like a magic ball that does the opposite of what it's supposed to do, right? So if this ball was here and you set it down and that ball always just tried to seek the steepest descent, then it's something, right? Like maybe the hill goes this way. It should go there, right? If you take that and like cast that shadow down to the ground, you're going to get a vector on the ground that's like pointed in that direction. And that direction on the ground, I don't know how to, imagine I'm standing on the surface, right? That's me standing here. Right? And I'm sitting there and I want to go and take a step to the steepest, right? Steepest descent. So that I've got to turn somewhere, right? And I've got to go that direction. Whatever that direction is, if you take that direction, you just like cast that shadow down to the ground. That's the vector field on the ground. And for every point, I would have a different vector on the ground that would take me in the steepest ascent. And that all those vectors on the ground, if you wanted to draw them, that's how you draw them. That's the vector field. So we're done. That's answered. Now, everything I just said is this picture right here. If you're standing somewhere, no matter where you are, it's going to give you some. This is like looking from the top down. This is actually just like a three-dimensional picture. I can move it, but it's,
Do we see the vector field on it?
Yeah. There's the vector field.
So the arrows point in the
Uphill, right? Uphill. The arrows point uphill, steepest descent.
So it's at its lowest point on the top and it's at its highest point on the bottom.
Yeah, if I go, let me see, if I move, let me try and move this point. Let me move it to right there. So where am I here? Yeah, it's hard to see it here, but move it back a little bit further. Right there. Okay. Oh, hey, what happened?
Didn't like that.
There, didn't like that. Okay, there we go. You see, if you were right here, do you see that you would have to, like this kind of arcs this way, like this. So you would have to head directly back to the origin for your steepest descent, right? You got to go back to the origin. And here's the top view. It's like I'm taking this and rotating it like that and looking at it like that. And that's the vector right here. It's saying go towards the origin to go your steepest. All right, conservative. Conservative vector fields. A vector field F is called conservative if there is some scalar function that generates that vector field. This just means the vector function is a gradient vector field of some function f. So go back to this right here. What was our answer? Our answer was 2xy, right? And then it was x squared minus 3y squared. Let's say I just came in and started class, or started today, and not today, but next class, and I say, hey everybody, is this a conservative vector field? You would say yes. I say why? And you said because last class we started with that scalar function and we created the vector field. If the vector field comes from the gradient of some scalar function, then it is called conservative. Yes?
Why is it a scalar?
This is called a scalar function because it takes in numbers and spits out numbers. That's what this does, right? You take in two numbers and it spits out a number. So scalars in, scalar out. This is a vector function because it takes scalars in and spits out vectors, which is why I need the vector arrow on top. So a gradient vector, a conservative vector field is a vector field that came from the gradient of a scalar function. And the question earlier was, can we actually go backwards? Can you start here and go back to where it came from? We will, just not yet. We'll do it very soon. That's it for 13.1. All right. Pardon? Yep, partial integration comes in. Do y'all want to try it? Do y'all want to just sneak peek at it? We can do it. It's not real hard to do. Let's do it. We'll get a sneak peek. We'll do this more later. This is definitely like a test type question. So the question would be this. Show that the vector field, what was it, 2x, y, and then x squared minus 3y squared. Show that that vector field is conservative. Right?
Could it be possible sometimes where you don't think it's a conservative vector field, like you make it a vector field or whatever, and then it turns out to come from somewhere?
Wait, say that again?
So like, let's say that you created a vector field.
Okay, so you have a vector field, just some arbitrary. Did it come from the gradient of a scalar
Yeah, so it just
function?
came from data that you have.
Yeah.
Is it possible for you to do this and still prove, and then it ends up being like, oh no, it actually is a conservative function?
Oh, you mean we do this and we say, no, it's not conservative, and then do something else and find out it is?